Yo, what's up, guys? Welcome back. Episode 91 today. We'll take a look at the Pokemon of the day. We got a Cloyster. Classic Pokemon. Let's take a look at the sound. Whoops, we need the sound. Yeah, let's take a look at the... we can just do the cry, that's fine. That's our sound, man.
Carp's signature summer ales. When friends gather, tradition.
Okay. Yeah. Good stuff. Okay. So, yeah, we're going to do a few problems. So, we're probably going to do something a little different today. We've been doing a lot of graph problems. I'm still going to do at least one graph problem today. But I'm thinking we kind of go back and kind of review a few other problems we've kind of done in the past just to make sure we still have that, skill there and we can solve those problems. I think that's probably the goal today. So what we'll do is we'll probably do we'll check out the problem of the day first, and then we'll do probably kind of like one of each problem. Count the number of powerful integers. It's a hard problem. Just send a text to my buddy really quick. Okay, let's take a look at this problem. Actually, it's called powerful if it ends with S, right? So what is our S here? It ends with 1, 2, 4. Okay, so we loop to the limit. Okay. Part of integer x is called powerful if it ends with S. In other words, S is a suffix of X, and each digit in X is at most limit. And each digit X is at most limit. Okay. Okay. What is the intuition here? I desire to skip this problem. Dynamic programming. This is done. I think I can easily do this problem, but in terms of making it fast, I don't know. Let's attempt it anyway, right? Just for fun. We can do a while. We could do a 4 too. We could do, well, I in range length, in range finish, but we go from start. Okay, from start to finish. We check, okay. We probably want to pull the last 3 digits, right? So we can do, well, slice is equal to, no, sorry. Let's do current slice is equal to, I know this is not going to run. Obviously, we need dynamic programming. I just want to solve this problem just by itself, and then maybe we can implement some sort of dynamic program. We can look up kind of how to implement it. We take our current slice, which would be, we'd go from probably need to take the length is equal to the length of S. So then we can go, well, we can do length. Sorry. If the length let's do num. Let's do cur length is equal to num.length. Right? So if cur length is greater than or equal to length, right? Then we can take the current slice, right? Because then the current slice is valid. And we go from, well, we'd want to take the last 3 digits, right? So we'd want to do, well, cur length minus length. And then we'd want to go to the, really the end, right? So I guess like that. Then we'd want to do, okay, well, I'm going to go for I. It's making it n squared now. For I in range, want to go from the length of, for I, nums, right? We want to check, well, Actually, no, let's not do that. Let's do, okay, we get that, right? Then we want to check, well, if current slice once it never enters the if, it's never going to get a current slice. So let's create a separate function, like we can call it check limit. Say like def check limit. We pass in our current num, right? And we would check, well, for I in range length num. Probably want to pass in our limit, right? If num I we don't want to pass in every single number, right? Like okay. So we're passing in, currently we're passing in a num, right? So probably need to break that up, right? So how to loop through an integer in Python. No, we want how to loop through each character in an integer Python. Turn it into a string. Okay. Maybe we can do Maybe we can convert it to a string in the thing. I guess we can just convert it here. We can just do string num is equal to string num, right? And then loop through, we can do, well, for char in a string num, then we can check, okay, if char is greater than or equal to, char is greater than num, sorry, if char is greater than limit, right, we can simply just return false. Otherwise, we just return true, right? We can call this function here. I'm going to get rid of this for now. Okay, and then we can do an if statement, and we can do, okay, well, if current slice is equal to I guess we have to first, okay, wait. I realize we're not going to be able to loop through this integer, right? We probably could convert it to an integer first, right? Get its length. So we call it string num, right? Get the length of it. We can get rid of this. We pass in a string num. We get the current slice, right? Can we slice strings? I'm sure you can, I think, but, right? And then we check, well, is the current slice is equal to let's do string current slice equal to string s, right? Right, and check limit. All right, I think that's how you call a function. Maybe you need a parenthesis, dude. I get confused between all the languages, right? And check limit. Check limit. Is equal to true. Then we just pretty much we have a count. There's no way the problem's a CD, bro. Like, and we can count plus equal to 1, right? I think this has to be before. We add this here, then we return count. Oh my god, I got string num dot length. Alright, this is meant to be the length of string num, man. I'm thinking Java, bro. This is what happens when you work with too many different things. Like, apparently it's minus length here. We need the inclusive range. The length of string num. Greater than or equal to the length. So we had originally. We slice. Then we check this if. If current slice. Sorry, if. Is equal. Well, S is already a string, so I don't know why I'm comparing it. And check limit string num. Alright, we don't have the equal to true. Then we can count. Return count. Oh, whoops. Got the string num here. Gotta tell it what we're slicing. Check limit is not defined. Whoops. String and int. Oh, we have to convert this to an int. Int char. Oh my god, dude. String and boolean. Oh, this is meant to be a double and. No, that's Java. Oh, it's meant to be like this. Okay, so we did do it, right? But the problem isn't that easy, right? This isn't gonna accept, I don't think. I mean, yeah, there's no way it accepts, right? I mean, it's way too slow. So now we gotta think of a way, well, how can we make this faster? To be honest, I really don't know. I don't know how we can make this faster. What sort of data structure can we use to make this faster? Well, maybe a speed up would be... Yeah, I don't know. So I was thinking about the right thing. We could do digit by digit generation. So somehow we could check if every number of the range ends with the required suffix somehow or contains digits that are greater than or that are less than limit. Um, okay. How can we make this faster? Leetcode didn't do it. What is going on here? But no way this guy's using a graph, bro. Wait, what? Tilly. Think about a possible range of integers and then build the DP from that. Solve with binary searching numbers and base limit. This is torture. It's not even hard, but really annoying. That's crazy that you can use DFS or BFS to, instead of checking every number start to finish, only consider numbers that end with the exact string S, have digits greater than limit. Yeah, I'm not sure, bro. I don't know how I would solve this Naruto video.
Welcome back, Shinobi. Today we're diving into another Leetcode mission from the Hidden Leaf Scrolls. This time, Lady Tsunade herself sent us a problem. Number of powerful integers. Sounds like a jutsu, right? That's because it is. Let's break it down using chakra control and real shinobi logic. Alright, listen up, Genins. We're given a mission to count all integers in a given range.
Jesus, man. Just break it down to Rudo style. Yeah, we're gonna leave this problem. Actually, let me look at the code, actually. Bro, I don't even know what this is saying. Like, DP, this is some sort of string comprehension. 0 times 2 for every number in range n plus 1.
Range that fulfill two ninja rules. 1. Every digit must be within your chakra control, meaning each digit limit your chakra limit. 2. The number must end with a specific clan symbol, a fixed suffix like 124, 10, etc. Let's decode this using some chakra-charged examples. We want all numbers between 1 and 6,000 that end with 124 and don't lose chakra control, meaning all digits must be Tuka 4. Let's try building chakra-strong shinobi IDs. 124, 11124, 2 and 24, 3124, 40124. But 5124, why? Because 5 exceeds the chakra limit. So answer, 5 powerful shinobi IDs. This time we're in a smaller battleground. From 15 to 215, we need IDs that end in 10 and are chakra safe. 110, 210. What 3 is fine, but it's not in range. Final answer, 2 strong candidates. This is like trying to summon the 9 tails with a weak ceiling jutsu. We want suffix 3000, but all our numbers are less than that. So none of them can even hold the suffix. Answer? 0 powerful integers here. Now, how do we solve this without brute forcing through all chakra IDs? That's troublesome. We'll use a reverse chakra build strategy. 1. We treat each number as a prefix plus suffix. 2. The suffix must match the clan symbol. 3. The prefix must be filled.
Okay. We're going to solve a different problem. Must do list for interview prep. Okay. So what we'll do here is... Okay, we've done these ones. Intervals. Stack, linked list. binary tree general, binary tree BFS, binary tree graph general, graph BFS, tree backtracking, divide and conquer, Cadene's algorithm, binary search, heap, bit manipulation, math, one-dimensional DP, multi-dimensional DP. Okay, so we've gone about 36 minutes on that problem. So what we'll do is we're going to do one problem from each, right? So let's start off with an array string problem. We'll do this one. I haven't looked at this one before. Move duplicates from sorted array 2. Given an integer array num sorted in non-decreasing order, remove some duplicates in place such that each unique element appears at most twice. The relative order of the elements should be kept the same. Remove some duplicates in place such that each unique element appears at most twice. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array nums. More formally, if there are k elements after removing the duplicates, then first k elements of nums should hold the final result. It doesn't matter what you have beyond the first k elements. Return k after placing the final result on the first k slots of nums. Don't allocate extra space for another array. You must do this modifying the array in place. The judge test your solution with the following code nums. Expected nums. Remove duplicates calls or implementation. Okay, so we have 1, 2, 2, 3, so we need to remove 1. Your function should return k is equal to 5, with the first 5 elements of num being 1, 1, 2, 2, 3, respectively. Doesn't matter what you leave beyond k, hence there are underscores. Okay. Okay. So I'm guessing we remove. Do we have to do this in like. Can we use like a hash map, or do we have to do this like? Oh, don't want to read spoil. Okay, I need to fully understand the problem first. AD, remove duplicates. Okay. So apparently the optimal approach here is a two-pointer technique. Okay. That's why we have 2 pointers. Okay. How can we do this with a 2-pointer technique? Okay. We have to solve it in place. So to solve this in place, I in range length nums, right? We need to keep an I pointer that iterates, right? And then a J pointer somehow I feel like we need to count these, right? If we get to a specific value and it's greater than 2, right, then we can overwrite this value and move 2 here. That's what I'm thinking, right? So we loop through here, we check, okay, once we reach a value, right, we keep track of some sort of value, right? Right, so we're gonna need some sort of J pointer, right? Let's say J is 1 ahead of I, right? We loop through I, right? And we go, well, I think we need to make a first value. So let's do, okay, value is equal to nums 0, right? We have that initial value, right? And we do, okay, well, if value is equal to I, probably want to start at 1. No, we can start at 0, right? So if value is equal to I, we can do, well, have a count variable. Right, value is equal to I, we increase our count. Count plus equal to 1. And then we check, well, if count is greater than 2, then we need to do some logic here, right? Do some logic here, right? Otherwise, else, if it's not, then we make value equal to nums I. Yeah, now that I realize this needs to be nums I, right? Value is equal to nums I. And then we make we obviously have to reset our count to be 1, right? Count is equal to 1. Because we're going to count that value that we're at, right? The logic that we want to do here is we want to check, well, let's call fix array. We pass in our current value, which is pass in I, nums I, and our array, right? Then we can go up here. There's some helpful function here. It's very well def. Fix array. Pass in our index, our value, and our nums, right? Okay, well. Do we need a helper function here? we get to this value here, and we want to move this. We want to delete this value. Pretty much want to delete this value and then move it to the end of our array, right? Delete value in Python. Delete value in Python using index. Delete -2 deletes the element at index 2. Okay. So let's delete that value. Okay, we want to delete that value. So at nums. Okay. And then we want to nums.append value. Probably didn't need an actual array to do this, but I think it still works anyway, right? So we call fix array, right? Okay, so now technically what we have here, we call fix array, we pass it back, and then we make count minus or equal to 1, right? Because technically we're at that value again, right? And then pretty much I think we would just return actually, I don't think we use a for, right? Because then there's for, we're going to keep going, we're going to keep going. So I think we need a while here instead of a for. So while I is less than you need to start with our I here. So while I is less than the length of nums, right? Let's actually create the length right now. Length is equal to length of nums. I don't know if it dynamically applies each time you call the while loop. So let's do while I is less than length. Okay. We call this if. While I is less than length. We need to do -1, so it indexes while I is less than or equal to the length. Okay. Then we want to go if. Is this wrong, dude? We're not even using a two-pointer solution here. We're not even using a J. Exactly, we're popping. Alright, so we want to probably have a K value. Alright, because we want to return our K. But now every time we call fix array, we want to K is equal to the length of nums, right? But now we want to decrease k every time, so k minus equal to 1. Can't access local variable count. The fuck? Why? I thought we were returning a k, dude. We're returning the array? Why is my array all zeros? Oh my god, the loop never advances. The fixed rate function doesn't do what it's needed. You always delete nums too. Oh my god. Bro, am I that stupid? Index. Right after each loop, we want to increment I plus or equal to 1. What is going on here? So there's an issue with changing the array in place, right? I can't be changing this array in place because it's fucking with the... Okay, we have a fast and slow pointer, right? Num's slow. If num's I does not equal num's right minus 2. But why are we checking the value? We're checking the value of num slow. Alright, so whatever value that we're at, if it doesn't equal num's fast minus 2, so if it doesn't equal that value, then we make num's right equal to num's I. Shouldn't it be if it equals? I don't get it. Check against 2 point position behind. Times 3 is equal to 2. Bro, I still don't understand. I is equal to 2. nums2 is equal to 1 and nums2 minus 2 is equal to 1. So duplicate we skip. I is equal to 3. We do nums3 is equal to 2, right? Yeah. Nums right minus 2 is equal to 1. Okay, write it. Bro, I don't get this. I generally don't get this, and I'm feeling kind of... Nums right. Sorry, nums fast is equal to nums slow. Slow plus equal to 1. Sorry, fast. Turn the index value. But how, dude? I don't get this. Like, we have a slow pointer. We have a fast pointer. If nums slow does not equal nums fast minus 2, nums fast, so dude, I'm just so tired, dude. Like, Jesus, man. Bro, this is taking me forever to understand this, bro. What the? Nums2 is equal to 1. Nums I is equal to right minus 2, 1. Too many skip. Right stay at 2. Okay, I'm gonna turn this around to make this more right. We have I, right, 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 right. Okay. Nums I is equal to nums right minus 2. Okay. Nums 0. Okay, so we skip it, right? But we keep. So now our I is at 2, right? Now our right is still. I'm trying to do it in my head, but let's just do it on Paint. Oh my god, dude. This is so stupid. Can't believe I can't understand this. Okay, so it's just like one for loop and one if statement, bro. I think it's because I'm tired, but okay, let's put in. Okay, we're looking for 1, 1, 1, 2, 2, 2, 2, 2, 3. Okay, we loop through and we go, okay. For I and right to length nums, we go, okay, right. Start at 2, right? So okay. So our okay, we start at right, right? So right is 2, 0, 1, 2. So this is where we are for I, right? I is here. Okay, and we go, well, if nums I, 1, does not equal nums right minus 2, which is 0, right? So comparing here, 1, 1, right? Then we skip, right? Nums right, we would skip this, right? Because they're equal to each other, right? So then we'd move I here, okay? So then we have, well, for I nums range, we start at right and we go to length nums, right? If nums I, this is I, so 2 does not equal right minus 2, so we're here. Okay. Then nums right is equal to nums I. Nums right, so this is right here, is equal to nums I. So we got 2 here. 1, 1, 2, 2, 3. Okay. That's wrong already, bro. Like, what? Nums right. Oh my god, dude. Jesus, man. That's where I'm getting it wrong. Nums right. Which should be 2, right? We're indexing the value, so we're looking here. Nums right is equal to nums I, right? So then 2 would go here. So we'd have 1, 1, yeah, 1, 1, 2. Ah, okay. Right plus or equal to 1. So now right would increase to here now, right? Because now we're at 3. Okay. So then our I, this would be our right, and our I so now we're at here, and we check, well, does I is equal to that, so now we'd skip over it, right? So then we check, okay, we're at 3 now over here. Check, well, nums I does not equal nums right minus 2, so then nums right, so nums 3, this one, is equal to nums Jesus, man. 0, 1, 2, 3. One, 1, 2, 2, 3. I've got 3 here. I've got 1, 1, 2, 3, 2. Okay, let's go through it again, right? So we have so our right is currently here, right? Which is 2. Okay. We check, well, if nums I does not equal right minus 2. If nums I does not equal, it does, right? Sorry, it doesn't, right? So then we move to the next value, right? So now I is here, right? And we see, okay, we have 4i in range right, like nums. If nums I does not equal right minus 2. So we're comparing 0 to 2 to 3, technically. Well, the index value. So we see it's not equal, right? So then we make nums right, which is this one. Nums right is equal to nums I, right? So then this one is now 2, right? And now right moves here. Now we check here. We're at I. Okay, so now we check, okay, well, for I in range right, make nums. If, well, now they're equal to each other, right? So we don't move. Now I is over here. And we're comparing these two. We make nums right equal to nums I. So now right, this is 3. We move right over here. Right, so now right is technically here. Then our I is invalid, right? So then we'd return 1, 1, 3, 2. But we're wrong though. Can we actually print out nums after every time, after every for loop? Great, that doesn't help either. Bro, what a confusing problem, bro. Like, times equal to 0, current is equal to 1. For I in range 1. Like nums. If nums I does not equal I minus 1, times 0, nums current is equal to nums I. I do not like this problem, bro. To be completely honest. I'm still getting confused with this problem. Like, it's pissing me off. Okay, let's do this one more time. I'll do one more shot, right? Okay, so our num is 2, right? So we have our right is 2. This is our index. We start at index I here, right? And we compare, okay, does this and this one equal? Yes, they equal. Okay, so I moves here, right? Now they check, okay, does nums I does not equal nums right minus 2? Well, it doesn't, right? So now we make nums right is equal to nums I. So we're at 2. Here we make nums 2 equal to nums I. So this becomes 2, right? So this becomes 2. Our right increases by 1. Okay, we're at the end of that. Now this is 2. Now our right is here. Now I compares over here, right? So now I, right minus 2. So now we're comparing 2 to I minus 2, right? So we're comparing to 1. So it doesn't pass again. So nums right is equal to nums I, right? Nums right is equal to nums I. So now this is 2 as well, right? Then we move right plus 1. Right goes here, right? Then we move I over here and we compare, okay, 3 is, we're comparing it to 2, right? Right minus 2. Right is currently at 4, right? So we are comparing it to here, right? But it's 2. We compare it, we realize it's not together, then we make this 3. Okay, move our right pointer forward. Then our I goes over here, right? So technically we return 1, 1, 2, 2, 3, 3. But we cut off this one, right? And technically return 1, 1, 1, 1, 2, 2, 3. Okay, so we got it. We understand now, but that was... definitely wouldn't have thought about that. Obviously, well, if the length is less than 2, we would just return like what, 0 or something, I think. Oh. the length of nums. Nice. Okay. Well, that problem took a little bit too long than I thought. Okay, let's do a two-pointer problem, right? Two sum input arrays sorted. When did we do this? October 15th, 2024. Jeez, man, that was a long time ago. Give it a one index array of integer numbers that are already sorted in non-decreasing order. Find two numbers such that they add to the target. Added by one as an integer. Find a blank two. Your test is generated such that there is exactly one solution. You may not use the same element twice. Okay. For I in range length numbers. For J in range length numbers, we want to start from 1. Right? Or we want to start from I plus 1 because we want to start from the same value. If I plus J is equal to target, oh wait, if nums I plus nums J is equal to target, we can just return I and J. Numbers. There must be some sort of difference here, like. Output, we output 0 and 1, but here they output 1 and 2. Why is that? Use only constant extra space. We're going to one index array of integer numbers that is already sorted and understanding how to find two now. Zero and 2 add up to 6, but they return 1 and 3. But one index array of integers of one index. Bro, there's no way we just add 1 to this. Like, there's no way. Like, there's no way. Like, right? There's no way this submits, bro. No shot. Time limit exception? I think so. Okay. Okay. So maybe this is the... But doesn't the O of n solution for two sum use extra space? We need TOE, doesn't need to be faster. Okay, so I believe, now that I realize, I think this is the 2-pointer solution, right? Like, yeah, okay. So we're going to need to do 2 pointers. By I is less than or equal to j, right? We said j, and we make j equal to the length of numbers, right? We check, well, how do we do this? We can't loop again. -1. Obviously, you have to initialize this to 0 too. How would we do this? Will we have to like slice some sort and like add up the numbers? The fuck, is this more of like a binary search? This is more like a binary search. Okay, current sum is equal to numbers left plus numbers right. Okay. If current sum is equal to target, we want to return the 1 base index, right? So it would be, well, I plus 1. Oh, sorry. We just return I plus 1, j plus 1, right? Otherwise, else if current sum is less than, they should have gave it away, right? It's sorted. Number rate is sorted, right? So we can, whenever we, they say it's sorted, you use binary search, bro. Oh my god. Else if current sum is less than target, right? Then we want to increase our I, right? So we do, well, I plus equal to 1. Else, we would decrease, right? We would do, well, j minus equal to 1, right? I believe that should return the answer. Left is not defined. Oh, whoops. Thinking binary search here. This needs to be I. This needs to be j. Can be whatever way you want it, but whatever. We have, oh my god, did I write right again? Jeez. Nice. Okay, let's do a sliding window. Given an array of positive integer nums, let's see what we got here. Jan 16th, we did this. Given an array of positive integers nums and a positive integer target, return the minimal length of a subarray whose sum is greater than or equal to target. Given an array of positive integers nums and a positive integer target, return the minimal length of a subarray whose sum is greater than or equal to target. Greater than whose subarray? Okay, I'm gonna go to the bathroom really quick because I have to go to the toilet. I'll be back in a second. What's up? I'm back. Back from the bathroom. Okay, so given an array of positive integer nums, and positive integer target, return the minimal length of a subarray. The minimal length. Okay, in this case we have 2 because we have 4, 3. The target is 7. Sum is greater than or equal to target. Okay. So let's create a res array. Let's do well for right in range length nums, right? We keep our left as equal to 0. Okay. We'll check well. I guess we can keep like some sort of cur value, right? So like cur is equal to 0, right? So then we check, well, we would add to cur each time, right? So cur plus or equal to nums right, okay? Then we check, well, if cur is greater than or equal to target, okay? When did we solve this, actually? Jan 16th. Cur is greater than or equal to the target, then we want to take the length, all right? We want to take the length, right? So we would do, well, the length is equal to right minus left plus 1. Okay. And then we compare, well, we do res is equal to max res length, right? Because we want to take the actually want to take the min, right? I guess. The min, right? Okay, and then I would assume after we take this res, right, what do we want to do? We probably want to do, well, if it's equal to cur, we have to make left plus or equal to 1, so move left up 1. And then cur minus or equal to left, right? Because we're moving left up by 1. Then I believe we would return our res. This needs to be float infinity, right? Okay, instead of the, guess we can do, this needs to be changed to a while. While cur is greater than or equal to target, we do this. We minus curve from left. Will that fix it? Return res if res does not equal none, else none, else 0. Return res if res is equal. No. Why does this not work here? Oh, that's what I'm missing. We're increasing left. Whoops. Needs to be before it. Okay. Return res if res does not equal none. Else. Okay, wait. Res is equal to none. Turn 0. I'll put null. Null expected 0. It's because it's returning a float infinity. Okay, return res if res does not equal float inf, else 0. Bro, there's no way that works. Like, oh, that's so sad. Um, okay. Let's jump through to the next problem. Interview top 150. So now we did 2.0, we did a sliding window, we have a matrix, hash map, stack, linked list, binary tree. Maybe we'll continue it for tomorrow. We'll do one more problem because I feel like we're getting kind of late here. Let's do Game of Life. Wikipedia, the Game of Life is known as simply as life. It is a cellular automation devised by the British mathematician John Horton Conway in 1970. The board is made up of M times N grid of cells, where each cell has an initial state live, represented by a 1, or dead, represented by 0. Each cell interacts with its 8 neighbors, horizontal, vertical, diagonal, using the following 4 rules, taken from the above Wikipedia article. Any live cell with fewer than 2 live neighbor dies, as if caused by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies, as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. The next state of the board is determined by the above rule simultaneously. Every cell in the current in this process, births and deaths occur simultaneously. Given the current state of the board, update the board to reflect its next state. Note that you do not need to return anything. It still interacts with its diagonal neighbors too. How the hell do we calculate its diagonal neighbor? I am not sure. Game of life. Let's check out the Wikipedia article. Conway's Game of Life. Okay, the board is made up of n-times grid of cells where each cell has an initial state live, represented by 1, or dead, represented by 0. Do not return anything, modify the board in place instead. Rows is equal to length board, right? Cols is equal to, or the length of the board 1. Let's print our rows, and let's print our columns. One, 2, 3, 4. Yeah, our cols are here. Okay. 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 I'm just not sure how we calculate diagonal values, right? Because, okay, here's 0. Okay, so maybe we can go, well, okay, let's make like a directions array, right? Equal to, we go, what is it? To go left, we would go -1, 0. To go right, we would go 1, 0. To go one, 0. To go up, we would add 1 to go up, right? Go 1, 2, 3, 4. So we would go 0. Let's go down first. And then to go down, we would go 0, 0, 1. Then we have to think about all the diagonals, right? How the hell would we go diagonal? Well, if down is this, then I think we go 1, 1, right? No. Actually, now I can think about it. Let's say this is left, right, up, down, then up left. We'll do up left, up right, down left, down right. Okay. So to go up left, right, we would have to go, well, we have to go, okay, to go left, we'd have to go -1, right? So -1 to go left, and then we'd have to go up 1, which would be up would be -1, right? Okay, I think. Up would be -1, left would be -1. Okay. Then to go right diagonal, we would go, well, right would be 1, -1, right? Then to go to go down left, we'd have to go down left, right? So we'd go, well, I know we'd add 1 to go down, right? And then to go left, we would -1. Okay. And then to go down right, we would go, okay, well, down would be will be 1, and then to go right, it would probably be 1 again, right? So this is our direction array, right? So then we go, okay, like 4i. I guess we could kind of perform BFS on this technically in a way, but for I in range length nums, in range, let's do rows, and for j in range cols, if, let's do, okay, for row in col, right, we can check, well, if board row col is equal to 1, right? Any live cell. So a live cell is 1. So it's equal to 1. And less than 2 live neighbors dies. Any live cell with fewer than 2 live neighbors. So fewer than 2 live neighbors equal to 1, then we count. Count is equal to 0. Then we do, well, we'd probably want to, we'd have to loop through our direction. So for dr, direction grow, direction call in directions. God, this is going to be a we do new row is equal to dr plus row. New col is equal to dc plus col. Then we do, okay, well, if so this would be a live cell here, right? We do live cell. Here we check, well, okay, if Um, and is less than is less than the rows, and 0 less than or equal to, and C less than cols. And so it's inbounds, and it has and board and C is equal to 0, because it has to be a dead cell as well. So 0. Then we count plus or equal to 1, right? And we get through here, right? We finalize its count, right? God, this is going to be a slow ass solution, dude. When we finalize this count, we check, well, if count is less than or equal to 2, fewer than 2 cells, fewer than 2, so that doesn't include 2, right? So if it's less than or equal to 1, then any live cell with fewer than 2 live neighbors dies as it's caused by underpopulation. Then we make, okay, grid, sorry, board, row, col is equal to 0. We do else if count is less than, if count has 2 or 3 live neighbors. If count is equal to 2, or count is equal to 3, then board, row, col, any live cell with 2 or 3 live neighbors lives on to the next generation, so we don't have to do anything, right? Okay, so then we do, okay, else if count is any live cell with more than 3 live neighbors, if any live cell with more than 3 live neighbors dies as if by overpopulation. Okay, so it's greater than or equal to 4. Then board, row, col is equal to 0. Okay. Then we need to do, well, else, right? It could be equal to 0, right? Any dead cell with exactly 3 live neighbors becomes a live cell. Okay, else, right? We have to do this as well. So 3, we have to check, well, count plus equal to 1. Then we have to check after, well, okay. You have to check, okay. Why is this messed up? Okay, we have to check, well, if count, right, if it's exactly equal to 3, exactly 3 neighbors. Count is equal to 3, then we do, well, board, row, col is equal to 1. right? Here we go through. No, you do not need to return anything. Okay. Let's see what this does. I'm definitely going to have some sort of error. Cannot access local variable count. Oh, whoops. Shit. Count is equal to 0. Okay, well, I did something wrong here. I could have done this horribly wrong, or did it right, but I think it's right. Oh. We're not assigning anything? Oh my god. Making it equal. This needs to be equal. That's why I didn't do anything. Okay. We are getting somewhere. Did I do this right? -1, 1, 0. 0 minus 1. 0, 1. Minus 1. 1 minus 1. Wait, fuck me. Hang on. 0, 1. Minus 1, yeah. 1 minus 1. Okay. Minus 1, 1. Yeah, and 1, 1. Okay, so I did that right. Okay, that's good. For round range calls, okay. Okay, so they pretty much want me to first... We've got the same thing. Okay, what am I doing here? So I've got a count condition. The count. Okay, board updates in place. You're modifying the board while checking it with these conflicts. This is because you're reading the original values of the cells while also updating it, so the future of the state of the board will be inconsistent. You should calculate the new state of the board without modifying it during the counting process. In the code, you're counting dead neighbors and using this count to determine whether a live or dead cell should change its state, but the rules should be based on the number of live neighbors, not dead ones. Okay. So determine the future state of each cell. Okay. So that's what we do here. Okay, we can get rid of this. Make some modifications, right? Right, we count, okay? For DRDC in directions, right, we make the count here. Count is equal to 0. Okay. Alright. Then we do, okay, NC is equal to this. 0 less than or equal to NR less than rows. And 0 less than or equal to NC less than calls. Board NC. Want to be checking, okay, if it's equal to 1, right? Then we do count plus equal to 1. Okay. So we're going through and we're checking the live cells, right? And board new row new call is equal to 1. Okay, we're only checking the live neighbors, right? That's what we want to check. Okay. So we loop through and we check, okay, if the neighbors are living, right? Then we add the count, right? So we're counting the amount of living neighbors, okay? Okay, so we got to the living neighbors, right? Then we check, well, okay, if board in the original row and the original column, original column is equal to 1, okay, then we know what to do, right? We do something. Then we check, okay, well, else if the board or the row, this could also be an else statement, is equal to 0, we want to do this, right? We want to do something, okay? And here we want to do, okay, well, if count is less than 2 or count is greater than 3, okay, we want to change them board, okay, row col is equal to 0. Ah, that's what I messed up, right? I was changing them to alive, but really technically when we kept looping through, it was affecting the other stuff, right? Okay. So then here, now we want to do world board. We want to do -1, which means it's alive. It was alive, but will die. Was alive, right? But will die. Okay, right? Then we do, okay, board row col is equal to 2, which means was dead, but now was dead, but will alive. I know it doesn't make sense. It should will be alive, but whatever. I'm gonna make it will alive just to, you know, keep it the same, right? Do that. So now outside of this for, right, the last step is we need to do final process and change grid, right? So we would go, okay, well, for row in range rows, for col in range cols, you would loop, okay, we check, well, if grid row col is equal to -1, right? So it was alive, but now it will die. Grid row col is equal to 0. Yeah. If grid row col is equal to 2, and grid row col is equal to but will be alive, so it's 1, right? And I believe that should work. Grid. It's meant to be, what is it meant to be? Board. 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 Nope. What do we got here now? -1, and we got we've got an if statement. Whoops. If the count is equal to 3, then we want to do this, right? This is in the 4. It should be outside. Because we want this to process, right? We want to process this 4. Okay. So we can go to the next value. And then we want to check it. And then go to the next value. Okay, we're still missing something now. I don't know what it is now. It looks right to me. God, I'm using another double equal somewhere. Equal to 2. It's so hard to spot those, bro. Man, the doubles equals and the normal equals really messed me up, bro. This needs to be else. Now, why doesn't it like it, bro? Like, what? If, else if. Oh, interesting. You're checking if a cell has board NR and C is equal to 1 to count its neighbors. But you should be counting live neighbors by iterating over all neighboring cells and updating them accordingly. However, when you mark cells -1 for live cells that will die and 2 for dead cells that will come alive, you should handle them properly in your final pass. What, I'm handling them incorrect or something? Like, equal to 1, equal to 2. Dude, what is going on here? It looks right, dude. Dude, that's what I'm doing. What is this talking about, bro? Okay, I'm just gonna copy this and see if this runs. Then I'm definitely doing something wrong. Okay, so this is wrong. So I've got something actually wrong here. Oh. Okay. 1, 2, 3, 4, 5, 6, 7, 8. What am I doing wrong? Okay. So we do the same thing, right? We have a count. NR is equal to row. Yeah, do that. If 0 is less than or equal to NR is less than rows, and 0 is less than or equal to zeros. If board is equal to 1. That's what we're missing. Why do we need those live neighbors here though? Why do we need this extra if? We check if it's 1 and we check, well, if it's was alive but will die. We check if it's 1 or -1. Was alive but will die. And and C is equal to -1. So we have an OR here. I'll put this in parentheses. See, does this run now? Now it does. We were missing this here. We were missing this check here. I was thinking about that, but I actually thought about this, believe it or not. But then I was like, you know what? I don't know. Maybe it doesn't really matter. Like, but now I can see why, because when we're switching these to -1, right, it's not actually counting if it's live. We're pretty much counting that it's dead now, right? Even though it should technically be live, right? So we should still be counting the live cells, right, as if they were live. So that's why. Okay. Oh. Now I've got an index out of error. Length board. How I have 1, it should be 0. There we go. I love these comments, bro. Like, They're so funny. Okay. Well, I'm gonna leave that, right? Tomorrow. Oh, it's not submitting them. Oh, it is. Okay. Tomorrow we're gonna do hash map. We'll do an interval problem. We'll do a stack. We'll do a linked list. We'll do a binary tree, a general one. We'll do binary tree BFS. We'll do a binary search tree. We'll do a graph problem. Right, and we're gonna keep going. Right, we're gonna go all the way down. We'll do one of each. Right, up to probably binary search, and then I think we'll probably start learning about a heap maybe, while continuing doing these graph problems, because these are important to keep learning. Okay, but yeah, sorry, I forgot to end the video. All right, appreciate you guys watching. I will see you tomorrow.